So this is us, also Serge Haziyev is one of the authors of this presentation. So I'm going to kick this off talking about our motivation, talking a little bit about why we created the game and yet another instantiation of the game. And then I will hand it off to people who actually know more about IoT to walk you through the steps of the game and the cards, and we've got some a demo, a participatory demo that you guys can get involved with. So motivation. The fact that you're here means that you already understand that architecture design is just one step in the architecture life cycle, if you will, and it's preceded by some sort of enumeration of architectural drivers, and once you do some design, presumably you might document some of those decisions, and having made those decisions, you might analyze or evaluate some of those decisions. And this is complicated by the fact that when you're doing design, you need to understand an awful lot about the domain, about the available technologies, and so we've done previous versions of our game with big data and machine learning, and today we're going to talk about how we've adapted and extended the game for IoT. So the game, and by the way, Umberto Cervantes was also involved in the creation of the game, follows the steps of ADD, the latest incarnation of ADD, which we call ADD3, and the central part of architecture design and of ADD is this step 4, which is choosing a design concept. So the architect, faced with the blank page, has to decide what architectural concepts, what patterns, what tactics, what technologies they're going to choose. And this is a difficult problem to begin with. It's a difficult problem to stay abreast of all of the technologies in a field. So this is how we conceptualize the architect's job. This is you in the middle. You're the crazy scientist, the egghead. And your job is to translate drivers into architectural decisions, documented decisions, hopefully. And what you're drawing on in that big head of yours is a set of design concepts, things that you know, things that you understand will help you to achieve those drivers. So that's actually the hard part, right? That's where a miracle occurs. And our goal in trying to create different variants of the game, in talking about ADD and teaching about ADD, is to try and make that part, that nugget of the design process, more transferable, more repeatable, so that it does not take you 30 years of experience and a lot of gray hair before you're qualified to be an architect. So we want to try and increase the adoption and the speed with which people can become this guy. So the game itself, we first presented this 4 years ago at SATURN, and our idea of the game, the idea to gamify the design process, was to turn design, something that is stressful and daunting and difficult to learn, into something that's maybe a little bit more fun, a little bit more lightweight, but still introducing the steps of ADD, the concepts of architectural design, and in a way that you could get quick feedback. So it's a game, you get a score, and that score tells you whether you did better or worse, and this can begin a discussion about how you do design and how you make design decisions. The game, certainly the first version of the game, is available at smartdecisionsgame.com, and that was the big data version of the game. Last year we presented a machine learning version of the game and did some demos and hands-on work, and today it's an IoT version of the game. So our objectives for today are to guide people a little bit through ADD, and that's certainly the objectives of the game. Perhaps more importantly is to introduce this notion of a design concepts catalog. The idea being that organizations can collect the knowledge, the wisdom of many architects, many years of architectural expertise into a corporate knowledge base about what design concepts there are within a domain and what they're good at and what they're not so good at along various dimensions of goodness, as you will see. So today we're going to show the instantiation of ADD for the IoT domain, and this is a domain which I'm guessing most of you don't have a lot of deep expertise with, and so this both shows the kind of generality of ADD and the modularity. There's a design process that works irrespective of the domain, and what you do is you plug different knowledge bases to different design concept catalogs into the process. So what I'd like to do now is turn it over to Sean, who will start to walk you through the motivation for the game.
Thanks, Rick. All right, so we talked about that we've done this with big data, we've done this with machine learning. Why IoT? Why do we want to talk to you guys about this year? One, I like IoT. I tend to spend a lot of time in the domain, so I'm really excited about it. But why should you be excited about it? Well, there's a guy who likes to put animals on books, and he once said that the guy with the most data wins. Also, that we think that's generally true, but what is really going to turn out is it's the guy that does the most interesting stuff with that data is going to win. But the important part is that you do need data to do stuff with. I'm sure the people here in this room, I'm sure all of you have some concept of what to do with data, but we still want to explain how this works. So if you think about the cost of data entry, if you think about the keynote from this morning about talking about maybe a decade ago, baseball was collecting maybe 1,000 data points per game. And if you think about how those data points were likely collected, there was a bunch of people making notes during the game about what happened, and somebody later has to enter it in. In the US, thanks to their good research, that a data entry job pays about $30,000 a year. Just to numbly type in data, which is great that that's more than we pay elementary school teachers. But what if we had automatic data entry? What if now that Major League Baseball is collecting 1 million data points per game, they're not keying that in, that's automatically collected through cyber-physical systems. So why is the IoT exciting? Why is it a buzzword? Well, the concepts have been around for a long time. It's really not that new. And the hype about it is maybe a little overhyped, but we're starting to get to the point where the economics make sense. The cost of sensors have dropped 3x in the last 15 years, largely driven by cell phones that have these really great little sensor devices that are quite reliable and also cheap and small. The other thing is disk storage has dropped 35x in the last 15 years. Then just in the last month, Google announced a new tier of storage that's 10x cheaper than their previous low-cost tier. So with all of these drivers, the cost of having that data is really, it becomes a business concern not to be collecting it. Just don't tell that to your GDPR consultants. So what are we going to do about this? Well, now that you guys are all excited that we're going to start making mountains of data from these sensors, how do we build a system? How do we do an end-to-end IoT system to collect this data? Well, we're going to make it into a game. As we showed you earlier, we've got some cards. So we're going to try in the next 30 minutes to prototype an end-to-end IoT use case that you guys are going to participate in. So for this game, you guys, all you architects that are used to wearing your architect hat, just keep it on. All the people who are here and working to be architects, take this as input on how you could do as a process. So if you guys should all have a deck of cards. If anybody doesn't have a deck of cards, raise your hand and we can make sure somebody gets that to you. Okay, so we've got one person back there. All right, so if you open the deck of cards, we've got this little pamphlet in front. This is your map. This is the key for the deck of cards. This kind of explains what are the different categories or pattern families that we've divided this end-to-end IoT system in. We've divided it into 5 different decisions that you guys are going to make. Then within each pattern family, we've got different options that you can choose from. If you look at the options and you look at the pattern families, you say, hey, Sean, this isn't enough to build an end-to-end IoT system. And I will answer you, you are correct. But we only have 90 minutes today, so we can't make every decision that you have to make. So these were kind of what we boiled down into what are architectural decisions? Well, decisions that are quite meaningful and could be hard to live with if you make them wrong. So what we want to do is we kind of identified in IoT systems, these are some critical pieces that you have to get right, or you'll get a lot of egg on your face when you go to release this publicly. You'll also notice within the different categories, this is not exhaustive of all the options possible. There are many other wireless communication protocols that we don't have included. There are a whole lot of databases that are not included in this list. We had to constrain the problem in order to make this game possible. So we decided we were going to constrain this to products within Google Cloud's stack and other main technologies that go along with that. Ruin the surprise. So we have the IoT cards. As you guys look at it, there's the protocol families, or the pattern families, and then there's the cards that have the detailed information of the patterns. And so we're going to play with these as we get later onto the game. However, to play this game, we need a real use case. The thing about IoT is it's somewhat abstract. Same thing with machine learning and big data. The reason that we like to build this into physical decks of cards is it gives you something tangible, gives you something to hold on to. It's no longer all the information that exists on Google. It's all the information that you're holding in your hands that you need to be able to be an expert of to make these decisions. The other aspect of it is that you do get something tangible to interact with on a very intangible topic. So now we're going to add one more level of tangibility and give you an actual use case that Yaroslav is going to talk to you guys about.
OK. So in order to prototype a use case, we need to have a use case. And when we were thinking about which use case to use for the game, we wanted something that everybody here could relate to, or at least feel guilty not relating to. All right? And so we chose the gym. Here's the use case. So I am the owner of a chain of gyms. And I have a problem, which is I have no idea how the equipment in my gym is utilized, which bears two more problems, which I cannot detect. I cannot detect the situation where my gym equipment is underutilized or overutilized. So why it's important to know? If my gym equipment is underutilized, obviously I miss on some revenue. I probably have some problems acquiring customers. And if it's overutilized, then my customers are not happy because they have to queue up to use a treadmill. And gym business is really competitive, and it's not good if your customers are unhappy. So that's the problem that you are hired to solve as an architect. So when you come on site to talk to the business owner, they reveal to you the scale of the problem. So they have the gym. This is not a single gym. This is a chain of gyms. And they have hundreds of facilities, of gyms all around the country, right? And every gym facility has a lot of equipment units, dozens and possibly, again, hundreds of them. And they really want to gather the data about equipment usage somehow, gather that data into a cloud system. We all live in 2019. It's all about cloud. And they want to know, they want to have insights from the data. So they want to see what the problems are with equipment utilization at this point. So that's the problem they're having, and that's the rough solutions that they are seeing. Right? So after you spend some time, maybe a week on site talking to the stakeholders, you kind of come up with a rough idea of the solution. So this is a MARKETECTURE. This is an architecture which is beautified and simplified. MARKETECTUREs are prepared by architects. And here's the main things you have been considering and talked about. So sensors. The way the customer wants to collect the data is to make a device which is attached to a piece of equipment and collects the data. So they don't want to use, they don't know how to use the actual equipment to generate the data, because some equipment can provide this information, some cannot. So they want to just solve it across the board and design own device that is going to report the data somehow. And they decided to use accelerometer-based device, which is a good idea because accelerometers, well, gyms are all about movement, and accelerometers detect movement. Also, they are cheap, and they are easy to understand. They are abundant, so accelerometer-based devices is a good option. But then you have to make decisions about the rest of the aspects. So first of all, your devices are going to relay the data somehow to the outer world. So how to do that? Well, obviously, we can throw the option of Ethernet cables or other wired connections out of the window because it's challenging to wire up dumbbells and stuff like that. So you will have to select a protocol to communicate information from the sensors to the edge or the lag thereof. So edge devices are the intermediate thing that relays the information from devices to the internet. And you can have edges and you can not have edges. That is actually something that's for you to decide. And we will talk about this a bit later. And then the information goes to the cloud where it's processed, it's stored, and it ends up in a processed form on the dashboards of the gym managers and gym owners for them to make decisions which gym facility has the most problems. This is the reference architecture which is completely oversimplified but usually an IoT solution will consist of those things: the device or the thing, the edge or no edge, and the cloud. So edgeless architectures, as I mentioned, are also possible, but not having an edge has its consequences, and we will discuss those consequences a bit later. Also, IoT architectures can have the fog element in it. And the fog is basically a beefed up edge, whereas it's not an edge device, it may be an edge data center, something big. But since the title of our presentation today is the Internet of Things Defogged, we will not be talking about fog today. So we are back to our usual three components. And this is the list of the decisions that you, as an architect, will have to make tonight. So let me make an overview about those decisions. First of all, something has to power your device, the sensor itself, and the radio that you will choose to be transmitting the information. Then, secondly, you will have to choose the protocol that the device will be used to communicate. And this entails two things. First of all, the logical protocol, and most importantly, the physical protocol. We are in IoT territory now. We need to care about physical things. So there are multiple physical protocols that we can use, and we will be choosing from them. Third option, edge or no edge, or which edge. And the fourth decision is the architecture of cloud processing. This includes the ingestion of information. And cloud database is about storage. So the last two options are actually cloud architecture. But we decided that having all of them would be way too much fun. So we will only take 3 or maybe 4 of those tonight. Cool. So let us consider, as the architects, the architectural drivers. So you're all well aware of the concept of the architectural driver. And the overarching drivers, which we'll have to consider in every step of the way, are cost of the device and the cost of and inconvenience of maintenance. So cost of the device is a pretty important thing because, as we remember, the scale is pretty big. So we are looking at 10,000 of devices, maybe more. So if you add $1 to the cost of any device, you're increasing the total cost of the architecture by $10,000. And the second item is maintenance. So whereas the first item is upfront cost, the second item is ongoing expense, which is also a very important factor. So please keep in mind those two things all the way to the end. And let us play a little game. So we are starting to reason about the architectural decisions that we will have to make today. The first is edge. So here are the drivers, the architectural drivers that pertain to the edges. Well, first of all, cost economy. Please consider cost economy. And it's kind of, oops. It's tempting to think that since I said that we can kind of dispose of the edge entirely, it's tempting to think, okay, so let's not bother with edge. Why it's needed anyway? It will save us hundreds of devices. But this may be viable or maybe not, because edges are actually useful for the following things. First of all, edge devices can seriously impact the decision-making policy in your solution. So you will have to make some decisions in your IoT system. And if you don't have an edge device, which is something usually connected to the mains and which has a significant processing power, you have only two options. You are either making the device on the decision on the device itself, which it may not be equipped to make because it's usually tiny and underpowered, or you make the decisions on the cloud, which means you go all the way to the cloud and back, and in mission-critical scenarios, this can introduce really significant latency. Processing on the edge is another important factor. So things like encryption or translating the protocols or intensive computationally intensive tasks are, again, not very well suited for the things themselves. And if you don't have edge device, you are most likely not able to perform those tasks. For example, protocol translation is essential because IoT devices, the protocols of IoT devices are not always IP-based. And if you want to relay the information to the internet, you will have to translate the protocol somewhere, right? And by the way, the edge computing technology has been evolving rapidly. And for example, Google has products that can significantly improve your options with edge processing, including machine learning and machine learning in inference and protocol translation. So I have just outlined the drivers, the architectural drivers for edge, which are commonly considered when deciding on edge architectures. Keep in mind that drivers may or may not be relevant for our use case and for our architecture today. That's up for you to decide whether or not each of those is relevant and will impact the result. Okay, so now you have instructions on your table which tell you how to join.
So this one's not on the table. This one's just on the slide.
Okay.
So this is the interactive part. We need you to participate. It's the end of the day. Maybe blood sugar's running a bit low. We didn't want you to sit too long without interacting. So as we make these decisions, you guys get to put your votes in so that we can keep you honest that you're actually participating in making these votes. So if you can go to this website, we're actually going to have you go to 2 different websites throughout the presentation. I'm sure most of you have at least 2 browser tabs open on your phone already, so it's not too big of an ask. But if you go to this URL with the hashtag IoT, when it asks you to enter the name, and then you will be able to vote on these questions, and we'll see real-time feedback.
Okay, so we'll give you a moment to open the page.
All right. And if you switch. All right, the code's back here on the left side of the screen. And you guys can use the cards, the deck of cards. There's information on those about the different edge categories.
Yes. So please use your architectural judgment and experience as well as the cards that are laid in front of you and contain the essential information to make the decision.
Yeah, the cards are also color-coded on the back. For the edge choice, these are going to be the red backs. Violet backs. Purple. Okay, got to study my color theory. Yes, the purplest ones. All right, do you guys feel like you need a little more time to process all the information?
Yeah, the numbers are still growing, so let's wait a bit more.
We'll wait for the long tail of the votes to come in.
Yep.
This is a lot like popping popcorn when you're waiting for that last kernel to pop before you stop the bag.
Okay. I think we can.
All right, any late stragglers, we'll count your votes later. All right, if we could jump back to the...
Yeah. So with architectures, there's no right answer, but we have some considerations about the options we have. And
if you guys disagree, if you guys have questions, I think we can get a moderator if it's really important. We are going to have a Q&A at the end, so if the question can wait, we can take it at the end.
yes. But if the question pertains to the game itself, you can't log in or something like that, then please go ahead.
Can you explain 1-star versus 3-star? We have a disagreement. Because if I were to look at cost economy at 1-star, that means it's bad.
Yeah, less stars is worse.
Is less stars is less economical.
Yeah, architects needs to fare good in ambiguous context. Yeah, so
I didn't read that, sorry.
that's okay. So the worst probably choice that we don't think would work is the no edge situation. And it's because, as we will see later, not having the edge will not allow us to make our devices lightweight and power efficient enough. So those of you who voted no edge are wrong. But we also have the most votes for edge with gateway, and it's a good solution because it doesn't only enable us to handle the scenarios, the processing and translation scenarios that we have right now, but it actually future-proofs us for scenarios that we have not been discussing with the customer yet, that will require more heavy processing or some fancy scenarios to implement. So, but this has also a drawback because this increases the cost of the solution, and you will have to justify the increased cost with your customer when you talk about your decision. But again, no right or obviously wrong answers here, because as we will see as we move, all those drivers or all those decisions affect each other, and something that seemed really correct right now can limit us in the future. I'm handing the clicker to Sean. Thanks.
All right, the next decision we're going to ask you guys to make is which protocol should we use to communicate this data? There's a handful of drivers for this use case. We're primarily looking to do occupancy, just a reminder, we're looking to do occupancy detection on equipment in a gym with an accelerometer, so we need to communicate some level of information based on that. As an architect, you have to decide what information needs to be conveyed over this protocol. So, then we did have 2 use cases that we really want to focus on. We want the real-time dashboard of what's currently in use, and the database at the end for what could then be used for business analysis and data scientist studies in the end. So with the protocol, what do we have to consider? Well, the cost economy of the protocol. And again, cost economy Fewer stars is less economical. But we have the cost of the radio itself. If you look at like cell modems, even the IoT-based cell modems are still in like the $15 to $20 range, where you can get all the way down to the really cheap Bluetooth radios that are coming out of China, where they're sub-dollar for your radio to do this protocol. Then for different other protocols, you might have knocking that off. For other protocols, you might actually have a subscription cost. For cellular, I'm sure you guys are all familiar with paying cell phone bills. That's the cost to get on the network. For IoT-based devices, cell companies have kind of gone with the strategy of just to have access to the network, even if you send 0 data, you still have to pay a subscription cost. Maybe $1 per month per device is a typical cost. But then you also have the cost of data. For any data that you then send is additional cost on cell networks and some provided LPWAN networks. Versus if you build your own Wi-Fi, Bluetooth, mesh network, you don't have to pay for the data haul if you already have a network connection. Other driver is bandwidth. How much data am I going to send? Am I going to just 800 hertz accelerometer data, I'm going to stream it raw so we can make some really accurate models about this thing. How much data do you really need to transfer? The other thing is, how often do you need to transfer it? If we only need this for business analysts, maybe we only need to send it once a week so they can generate reports. But one of the use cases, we wanted kind of a real-time feedback of what equipment's in use. Maybe if one piece of equipment goes not in use for a while, the gym manager might want to go check out maybe it's broken. Maybe as a gym user, the gym wants to present this information to their users so they can decide, I want to go to the gym that's got the treadmills open because that's what I want to do today. But also how often is it transferred. Even if you're collecting a small amount of data, but you only transfer it once a week, that could be a big burst. And if you're looking at like LPWAN, a lot of those low-power networks will only allow you to send tens of bytes per packet. So you're not going to be able to chunk out a week worth of high granularity data, even if it's a small amount of data into that packet. Then you have power efficiency. That's where this protocol uses its power. It uses its power to transmit when it's trying to reach the base, the receiver. When you think cellular, that could have to reach a long way to get to a cell tower. Cell modems are allowed to transmit up to, I think, about 1 watt of transmit power, so that's quite a lot of energy that it has to put into that antenna. Versus the smaller mesh networks, Bluetooth, lightweight radios. Then you have the receive power, which is how much energy it takes for the radio to be listening, for it to receive commands. Even though this device is only reporting state, it does probably occasionally need to listen for things like firmware updates for security patches. Even though that'll never happen, you'll write it just fine the first time. Then when you're not receiving, you've got idle power. That's when you're not actively sending or receiving data, but different protocols still are non-zero. When they're idle, especially like cell networks, require you to continually check in with the cell tower to let it know you're still there and negotiate. So even if you're not sending data, your radio might still need to be pinging to the network to make sure its keep alive is there. Then it brings us to sleep modes. That's when it's not pinging, it's not communicating, it's just sitting there asleep. One of the great things about some of the newer cellular IoT protocols is that they have extended sleep modes. That means the radios can go away, just turn off, they're not using power, and the cell network's not going to kick them out of the network so that they can still have a warm start when they boot back up. That's the real great thing about some of the new cellular IoT protocols. Then we have device density. How many devices are in the same area? If you're over at a Steelers game, you're going to have tens of thousands of people who are not going to go the entire game without checking their cell phone, that are all going to need service within that same little bowl, right? So that's a fairly contentious environment for the network space. Things like LPWAN are just not going to function with that level of device density. But if you're in an agricultural situation where you've got maybe a weather station out in a field, there's not going to be a lot of other RF signals that your protocol is competing for in device density. In our case, we've got a gym. It's probably a big enough space that you're not going to be able to cover it just with one Bluetooth signal. And you're not going to have negligibly small amounts of devices, but a few hundred devices isn't outrageous in this realm. Lastly, you have range, the distance between the transmitter and the receiver. How far does this signal have to go? The great thing about LPWANs is you can get multiple kilometers of range between your device and your receiver. And that is really cool at the trade-off of device density and bandwidth. But there's also the concept of mesh. So mesh is the idea that one device, even though it can't necessarily reach your gateway, another device could help it out and repeat that signal. So you can essentially increase the range of your network by having other devices repeat your message to create a mesh. The negative effects of that is that every time you have to repeat a message, that's more bandwidth of your network. So now it's not just the one amount of data you're sending, it's the amount of data you send plus the amount of data in each hop that has to take. The other negative effect of anything repeating that signal or any repeater in your mesh has to be always on and listening in order to hear the message in order to relay it. Now there are some other protocols that we're not really getting into that do advanced things with that, but in general that's the concept. So now we're going to make our second decision. If you guys could get your devices out and go back to the voting. You also have the cards in front of you. So the protocols are going to be the greenest cards. So this one's a little bit more complicated with 5 options in a space that's not necessarily as familiar for heavy software backgrounds. If we could, it looks like that's close to the number of votes we had last round, and it looks like there's definitely a clear favorite. I don't know if we had kind of tournament effects of showing the live scores. So if we want to go back. So if we look into this, one aspect that you might notice on the bottom of your card, of the protocol cards, is it says works compatible with edge. So in the first vote, we had a lot of votes for no edge because of the cost economy. However, anybody that chose no edge and then on the subsequent vote picked mesh, you might struggle because mesh is typically not an IP-based protocol that could go direct to the cloud. With mesh, you will typically need a gateway in order to relay that. That's something that we attempted to capture as a driver on the card, but is also really important for when you make architectural decisions. As we know, every decision you make potentially limits your options and future choices. So while mesh looked like a really great protocol based on the description in the cards that we gave you for this application, if you had already decided that you're not going to have an edge, that's really not a plausible solution in the real world. Now, also, if we look at this chart in the key, we actually introduced a new category of proto. What does that mean? Well, we talked about IoT. Part of doing this game, this is a prototype. But this isn't the only prototype you do in our architecture. Maybe the output of this game is identifying what are the next things you need to test. So we kind of said that cellular IoT, $15 to $20 per modem is just really not going to be feasible for the device. For broadband, for cellular broadband, we really don't need a 120 megabit connection just to stream this accelerometer data. It's not like 4K Netflix from this little device. But then we kind of, if you look, all the other ones actually have blue categories of proto. So there's not necessarily one that you can just say, this is the right answer, I'm good, I'm done, move on. What that means is that for our situation, the data is not entirely clear as to whether this will be a hole-in-one fit for your solution. So it means you might need to prototype it. But if you're prototyping this, what's really cool about this methodology is you don't have to build an entire prototype for every aspect of this protocol. So if we look at LPWAN, wireless LPWAN, we have bandwidth and device density. Those were kind of our concerns. Those are actually 2 things that we could easily prototype of, can we put enough devices in this network and still communicate? Can we get the data reporting low enough that we could still fit it into the bandwidth? One of the other things that we kind of said was Wi-Fi might not be a great fit. It might be okay. I saw in the voting, there was a few people that kind of thought Wi-Fi. And historically, Wi-Fi has been a pretty power-hungry protocol. However, this industry is changing all the time. Every month, there's new little Wi-Fi chips coming out of China that are for IoT devices and can actually run at quite low power if you write your code properly. So that might be something that a prototype, can you get one of these devices down low enough power in order to consider something like Wi-Fi, which would then open up your edge choice options. All right, so that we've kind of talked about that. And then we've got our next choice is what is we going to power this device with?
Okay, so we are down to power now. And so as you've noticed, decisions you make in the past can affect the decisions you will be able to make in the future. And those of the architects who selected broadband, LTE, or Wi-Fi may find themselves in a difficult situation right now because powering those protocols may be rather challenging. But let us move on to the drivers and examine the situation. So first driver is maintenance. Maintenance translates to cost. And basically, when you're thinking about maintenance, you have to weigh two options about the battery that powers your device. You can either go with a replaceable battery or a rechargeable battery. So replaceable battery is low maintenance because actually it's possible that you will never have to replace the battery if the battery is big enough and the device is economical enough. It draws very little power. It's quite possible you could build a device that uses a coin cell which outlives the useful life of your device, and that's okay. But that may not be possible if based on some of the decisions you could have made about the bandwidth or the sample rate or the protocol that you're going to use. Another option is rechargeable battery. It incurs the maintenance cost because you have to ask someone to go around and recharge those batteries, which may or may not be feasible. There are, for example, gyms that are open 24 hours a day, not mentioning the frustration and the cost of this operation. But it's too early to disqualify the rechargeable battery option because you have energy harvesting options, which means that your device is powered by the environment. And the environment in our case can be the light and the kinetic energy of the equipment itself. So gyms have the benefit of having pretty good lighting, and you can conceivably use a photovoltaic battery cell to recharge your battery, or use a piezo element to power the device from the movement of the gym equipment itself. Capacity is an obvious driver which is connected to the other drivers. It's the amount of energy you can afford to spend between the replacements or recharging of your battery. Mobility is also pretty important things. How mobile is your power source? So I hope you agree that immobilizing gym equipment because your power source is immobile is not an option. So your power source has to be at least somewhat mobile. You can argue that an extension cord is flexible and moves, but again, it introduces some inconvenience and safety hazards. So that's mobility. You have to consider cost economy, and with power sources, cost is usually the upfront cost of the cell or the battery itself, because energy is pretty cheap and you can neglect it in your calculations. And ruggedness. You know that electronic devices can exist in environments in which humans are not as good as existing, like high temperature, high humidity. But batteries are usually not. Lithium-ion batteries can catch fire if they are heated enough, which is not the case with supercapacitors, which you can pair up with a photovoltaic battery. And diversity of environments means that when you turn off the lights at night, your solar cell will not work. You know the drill, so please place your votes. Okay, thanks everybody for voting. Can we switch to the presentation, please? So this particular category to me feels like the one that would best benefit most from prototyping, because it's pretty hard to reason about the power as it's so connected to the protocol, to the physical representation of your device and other factors. But as I mentioned, mains powered option is probably not as optimal. We thought to to give it 0 points, but we afforded it 1 because it's still somewhat mobile. The non-rechargeable batteries and rechargeable batteries are also slightly suboptimal, but if you think about it, going with a pretty large non-rechargeable battery and pretty economical device with very low-powered radio could actually work. But again, as I mentioned, prototyping in real life, you would really want to conduct some experiments with actual hardware before committing to an architecture for your customers.
All right, and now we really wanted to get you guys out of your comfort zone, so we're going to talk about databases. Because I'm sure you guys are, just kind of looking at some of the nonverbal feedback, you guys, some of these questions caused a lot more thought, might be a little out of your expertise. And as architects, I'm sure you've never been asked to make an architectural decision about a topic that's slightly out of your expertise, right? Never happens. So we just wanted to give you something here at the end to maybe be a little more comfortable, feel a little more at home. So I'm not going to drone on about all these database drivers, because I'm hoping most of the people will catch on quickly. The one thing that might be new for some of you is we did limit this to Google's cloud database options. So people that aren't in Google Cloud might have to learn a little bit about just the names of the services. So with cost economy of the database, there are serverless options of scale to 0, don't pay when you're not using it. That's something that could be valuable depending on the use case. Storage, everybody knows you have to pay for storage in a database. One option on there that is somewhat unique is BigQuery, is Google's data warehouse solution. It actually has very cheap storage, almost the cost of their cloud storage itself, but you do pay for the processing that had to happen for your queries. So you pay essentially per query, which is an interesting dynamic on that database. Scalability, how much data are we going to have? If we think that we've got tens of thousands of sensors and we think maybe we want to retain this data for a year in accessible form that we could process, and then does it need to be distributed? We said we've got gyms all over. Thinking about the use case, thinking about the next category of performance, do we need the database to be close to where the data is coming in order to use it? Performance, we're not trying to spark a SQL versus no SQL debate. That's not the intent. We just want to say that both options are on the list for however you guys think is a good choice for this solution. And we think that specifically for IoT, there's kind of 3 different categories of performance that are important, is the ingest, the update, and the query performance of the databases. Very closely related to performance is real-time ingestion. It's a very common application for IoT that you've got these sensors, and you want to be able to act on this data in some fairly small amount of time. So that's kind of the time that it takes for the new data to get into the database to be acted upon. And then lastly, ad hoc analysis. Do you know everything that you ever want to ask about this data? Or are you going to be asking questions of this data that you haven't yet thought of so that you can't pre-structure your data in beneficial ways for that? So those are the drivers. We're going to go ahead. We'll jump to the questions. I think you guys are knowing the drill. Also, one caveat of this, if you'll notice, all the other questions we had 1 answer. This one, you'll notice you can put into 2 answers. Sometimes it's common to use something like a Lambda architecture where you have a warm path and a cold path because you might have different demands on the data. So if you think that's a good architecture and you really like that, we are going to open it up to be a little more broad on this vote. We're stuck at 49. We've had a little over 50 each time. Maybe some people just, they don't want to be held responsible for this decision. We hit 50, we'll call that good. All right, so now we can discuss. With databases, again, there's certain things that might work, might not. This, I'm sure you guys will have stronger opinions on maybe than some of the other technologies that you might not have been as familiar with. But our view, kind of running through the numbers of, if we have tens of thousands or 10,000 devices that are all reporting data at minute intervals, and we're going to keep it for a year, Cloud SQL runs on Postgres, MySQL. Those might not scale to have the amount of data that we want to keep in the database accessible. Also, depending on the amount of data in the database, the real-time ingestion will degrade as the database gets bigger on those services. Something like Spanner might be great, and it's pretty strong in like every category. However, it's not very economical, and we don't necessarily need the great benefits of Spanner in this case. So it's not a bad decision. There's just lower cost options to achieve the same end. Data store isn't very good at replication. And also, because it's a NoSQL database, a document-based database, it might not be easy to query after the fact, but it could be good for your warm path, depending on how much data we want to put into that. Then you've got, now however, we do have Bigtable, which is Google's very, very, very IoT real-time time series data database. It is quite expensive, so depending on if you think you need that, you might not need it. And then lastly, BigQuery, which is kind of like in chemistry, you can always convert to moles when you're struggling. And I think Google is a lot, when you're struggling with databases, you can always rely on BigQuery. Okay, so we've got some votes. We got a little discussion with this card game. So what about this end-to-end system? We talked about a hands-on demo. So we played this game with ourselves, and then we decided the outcome of this game that we played should be a hands-on demo. So we decided that we wanted to build a system that would monitor the usage of a device based on accelerometer data. So we made an app, because it was convenient that you guys all brought an accelerometer here with you that we could use to collect data from. So there's a card if you need a closer QR code. Or you can scan the QR code on the screen for those that are closer. So we've made this little game, a little hands-on demo that's going to collect data from your accelerometer, and then we're going to show it on a dashboard on the screen. Getting the device set up, the whole world of the internet about 5 years ago decided access to your accelerometer is totally fair game by all websites that ever want to use it with no permissions necessary. That was great. The world was a happy place. There was no data privacy from your accelerometer. But Apple thought, that actually could be potentially compromising data. So 4 weeks ago, Apple rolled out iOS 12.2. And in that update, they decided that access to your motion sensors would not be enabled by default if you're using Safari on iOS 12.2 or newer. For those of you that want to participate in this game, and want to use an iPhone, and want to use Safari, you might need to go to your settings in Safari and enable motion. That little card on your table is a closer view of if you want to enable that. Now, as motivation to participate in this hands-on demo, 2 of the participants that are playing today are going to be rewarded with a Google AIY dev kit. So you have a dev kit on Google AIY Voice and Google AIY Vision. All right, so we have a gym dashboard. So as you guys are logging on, we're going to have real-time data, assuming our laptop's Wi-Fi connection hasn't been dropped. Great. So as you guys log in, picking the username or nickname is anything that you don't mind us calling out loud. The gym location is totally arbitrary. It just made the screen a lot more interesting than if it was a single bar. So you guys pick whatever you're feeling like, whichever gym location's speaking to you, whatever piece of equipment you're in the mood to use today. So once you type that in, you're going to see a little graph on your screen. That little graph on your screen is the raw accelerometer data that's being pulled from your phone. We put a threshold on that and kind of said, if your accelerometer goes above this threshold, your device is in motion. And you're going to have you're going to have available go to occupied. So anybody using Apple devices that shakes it left and right, that's also the gesture to undo, so it's going to give you a prompt. I recommend up and down. You can also just sit it on the table and smack it. So if we look, with our gym chain, it turns out that the Bricksburg gym is just not invested in recumbent cycles yet. Nobody can use those. There's 0 in the total. But it also looks like all the other equipment that's at the Bricksburg gym is 100% in use. So if you guys have this dashboard on your phone, you're heading home, don't go to the Bricksburg gym right now. Okay, availability. The other thing that we're showing at the bottom of the screen is a historical view of this data over time. Because we are doing this demo, because everybody's playing with their phone, we're simulating the 7:30 rush hour at the gym. But so maybe this is a bit of a contrived demo. If we want to talk about the architectural decisions that we made in building this demo, we decided that we would use a rechargeable lithium battery, and that we would just make users recharge that battery when the battery ran low. We decided that we would use both a Wi-Fi and or a cellular broadband modem in order to collect this data. And the benefit of picking those two options was that it was all provided to us for this demo today. All right, the other thing we did, if you guys look at the URL, we built this on Firebase. It's all serverless. We've spent $0 doing this demo with a few hundred people now. It's quite a fun way to do this. And then to get the real time, we're syncing with a Firestore database, which is essentially a mobile version of Datastore. It's not going to scale to huge numbers, but we're not going to talk to huge numbers much bigger than this group anyway. All right, so you guys have been playing with the demo. We've kind of looked at this, and does this kind of, one thing that we like is that looking at this kind of sparks ideas. Like, so what can you do with this? Well, if you've got this real-time dashboard, maybe it's going to help me decide which gym location I want to go to on the way home. Maybe there's two locations that are about the same distance. Maybe gyms want to look at this historical data, and they kind of say, based on this historical data, we see that there's a lull in the afternoon at 3 o'clock. There's just nobody in the gym. Maybe we can come up with a new business model where we have a limited opportunity gym membership, where you can only go work in the gym from 2 to 5 in the afternoon. And it's extra low cost, but it gets them in. Being able to have this data, being able to analyze this, kind of opens up new business opportunities. This is just, fairly, it's just thresholded accelerometer data. Is that really that interesting? Well, if you feed this into a model, you might be able to build more predictive models. If you pair this with individual user preferences, you might actually be able to provide customized workout routines just based on this little sensor. So it's actually pretty impressive what business opportunities something like a simple little sensor like this could enable in a different market when used properly. All right, so we've been playing with this. The novelty is probably starting to wear off. I am impressed with how many of you guys are really sticking with that. All right, so now we're going to end the game. And when we end the game, you guys all watch that your app. 2 people are going to win a prize, and you'll be notified through your phone. Thanks for participating.
We have YC and UE.
And who is the other?
And Billy Memo.
Awesome. All right, thank you guys for participating with that. We're going to let Yaroslav wrap it up before we do Q&A.
Okay, so what are the main takeaways from this game? IoT architectures are just architectures, and the process of driving an IoT architecture is something that you all are familiar with. So when you are designing an IoT solution, you have to be pretty close to the physical world. You have to know your radios, your hardware, the main aspects of the devices you're building your solution from. Well, ultimately, it's a system architecture. So. And as you have seen today, you will be going back and revisiting and reviewing the decisions you had made before. But that's our job, that's our life, and actually the attribute-driven design methodology, which is championed by Rick and Umberto, equip us really well to do that and feel comfortable about it. But again, you can see that we did not provide you like true answers or completely false answers. It's all trade-offs. It all depends. It all depends on the details you will realistically be discovering as you work on the realistic task. Another takeaway is that prototyping is necessary to validate the decisions, and I think we discussed that in detail already. And think about having a design concept catalog for yourself, because it's easy to get lost in the sea of information you need to make architectural decisions. We hope that the IoT cards we presented to you today give you an idea of what this catalog might look like, or even you can use it in your actual work should you ever have to design an IoT solution. It's not nearly exhaustive and complete, obviously, but it's a start. At least you know the main concepts, and you can go from there. So thank you very much for participating.
Do you want to go to the next slide?
How has the introduction of 5G changed IoT options as far as connectivity and whatnot?
So that's a good one. Huge potential once something's concrete and exists. So right now, we've not had any real business applications where the deployment has been wide enough to utilize in a full end-to-end solution. However, there's lots of, some of the excitement about 5G is kind of the wire replacement. We've worked in kind of industrial applications where putting in a gateway on a machine, running an Ethernet cable, by the time you get the electrician, you get the scissor lift, you get the area closed off, you shut down the piece of equipment, you're looking at a minimum of $5,000 to drop an Ethernet cable to a machine. So if you can replace that Ethernet cable with a 5G modem so you can have really rich internet connections, that's a big game changer in a lot of applications. The other big application that we're really excited about is how it's going to affect autonomous vehicles and the amount of data that can be collected in real time from vehicles.
But there's also a trade-off. So there's a concern about privacy, because 5G is has much shorter range due to its high bandwidth, and it's much easier to triangulate your location for the cellular company without you accessing the internet, and some people find it disconcerting.
More questions?
Other thoughts? Anybody want to argue with our decisions?
SQL versus no SQL?
No.
Just short question: do you guys intend to add additional domains to the big data, ML, and IoT? And what would be?
Yeah, we were just discussing that. So maybe you guys can give us feedback, but we were talking just a little while ago about maybe a blockchain set of cards. Andre, wherever you are. No, a different Andre. But I don't see him.
I was thinking about machine learning, but putting into production, not the selection of the algorithms, but all the setting up of the
The pipeline.
the support of.
The MLOps?
Uh-huh. Yeah.
MLOps.
More questions? So I had one question. So from the choices that we made, was there like one block of decisions that were like the best overall, or not? Because in general, you were saying, it gave me the impression that there were several possibilities, but for example, in the big decisions game, it was more constrained and there was like kind of one solution. So
Yeah, for the big data game, we definitely had it a lot more quantified than we have this game. But kind of in this scenario, we haven't prototyped at scale enough to kind of see. We're within what we're doing, we've got a lot of research on like low power sensors within our R&D team. So the sensing, we know we can get low power enough, but it's more the details of the implementation of, would Wi-Fi make sense if a gym has Wi-Fi coverage already versus putting in a mesh network to cover the gym. So a lot of that is somewhat application dependent on the customer. But in kind of looking at our outputs, if we can get LPWAN if we can get the data low enough, depending on what the actual use case that a customer would want, LPWAN's a really good low power, low cost protocol. Kind of second, or really I think first of what our go-to thought would be rechargeable battery with a photovoltaic to power it, because gyms tend to have decent lighting. And then reporting that over like a Bluetooth mesh. One of the cool things with Bluetooth mesh is a lot of smart lights are starting to put in repeaters in the light itself. So none of our devices have to be a repeater, and there can be lots of lights, so you've got lots of repeaters for rich coverage within the gym.
Okay.
Going into the database side, once you get into it, BigQuery is really good for the ad hoc analysis. A lot of data science like it. It's got a fully SQL compliant interface, so it's really good for pulling through the data. Depending on the amount of data that would be generating for what we want to accomplish, Bigtable is good for the time series stuff, but might be a little overkill depending on how much data we have.
So to step back just slightly, to answer your question slightly differently, in a real world design context, you've got a lot of constraints. And here we're relatively unconstrained, and so there's a much broader space of possibilities. But when you're actually designing, it won't be so unbound.
Yeah, that's correct. Yeah. Any more questions or comments? So let's thank again Serge, Sean, Yaroslav, and Rick for their presentation, and Software for being sponsors for the conference.